This is more or less the evolution working on my transfer function. The first part, there is only C2 and the feedback path that makes the integrator. Then C2 short circuit with respect to R2, not an absolute short circuit, a short circuit with respect to R2. Then we have this constant gain. R2 and R1 is the gain, negative R2 or R1, but here. Then C3 starts to become short, starts to close, and here becomes a short circuit with respect to R3, but we will see in a moment. And here we have the gain R2 divided by R1 parallel R3. And here in the last part we have an integrator, and there is just a C1 that is dominating the feedback range, and here there is R1 parallel R3. And the two equations that we derived up to this point is that Fp2, this pole, is equal to, like in the type 2 compensator, 1 over 2 pi C2, C1 R2, and Fz1, and this is my choice. I assume that the first 0 is given by C2 and R2, Fz1 is equal to 2 pi C2 R2, and then we have the two gains collection. Problem is, what the zero and pole frequency, how is this zero and this pole frequency, how these frequencies are related to the components? Well, there is a straightforward way to find it. It's just to write down your equations. Parallel, series, ratio, etc. You find it very easily. Or we can look at the circuit and write down at least the pole frequency. Pole frequencies are easy to determine because it's just a C times the equivalent resistance. Zero frequencies are a little bit more complicated. So, let's go to see what the pole frequency associated to C3. R1, C3, R3, and here we have R2, C2, and C1. Looking for the pole given by C3. This is a third order system, three poles, three capacitors. Do these capacitors interact with each other? Well, these two interact, but we know that the C2 is quite larger than C1, so we just simplified our expression to try to compensate. Does the C3 interact with C1 and C2? Does the C3 see a change in impedance, in its equivalent impedance, if C1 and C2 become a short circuit or open circuit? This is the interaction. Do they interact? No, because the voltage over here is 0 volt for signal. It's a constant DC voltage. So we have a 0 volt, and my C3 R3 block becomes just C3 R3, and here there is R1. Here there is a signal source. There is the output voltage of my system, and here there is my input, my op-amp input, that is a ground, as seen from C3. It's not an actual ground, it's just a virtual ground, but C3 does not see any difference. C3 sees that this point is at 0. So we have 0 voltage over here, constant voltage over here. What is the equivalent resistance seen by C3? That means we remove C3, and what's the resistance seen by C3? Remember, C3 does not interact with C1 and C2, so this is an exact way.
R3.
R3, nothing else. This is R3, just R3 is seen, because on this side there is a ground signal, and on this side there is a ground. So, the pole associated with the C3 is just Fp1 is just 1 over 2 pi C3 R3. Okay? So now we know this pole, this 0, the two gains. I would like still to have the 0, the frequency of this 0 related to the components, so my design can be easier. And finding zeros is always a pain in the neck, because some cases are difficult, in some cases are even worse. Here, you could find more or less where is this 0, because what does the 0 mean? Transmission 0 means that there is nothing at the output. There is 0 voltage at the output. So in order to get a 0, transmission 0, to have nothing here, even if you put a voltage over there, it means that either you have to have Z2 that goes to infinity, that's not the case, or you have to have here this impedance going to, I made a mistake, sorry. Either you have to have Z2 going to 0, how to get the output resistance null, or you have to get here an infinite impedance. So the 0 of this transfer function can be derived saying that Z1 that is equal R1 parallel to R3 plus 1 over SC equals infinity. Any mathematician over here? No mathematicians? So I can write equal infinity. That is just awful, because infinity is not allowed. So you solve this expression, you find out what is the S value that makes this expression infinity, and you get the 0. Or you can say, okay, I know the transfer function that I get. The transfer function is here around, the transfer function has a pole that is 1 over 2 pi C3 R3. I have a gain over here that is R2 or R1 parallel R2, 3. I have a gain over here that is R2 over R1, this is negative and this is negative. I know the two frequencies. I know two gains. No, I know two gains. I know one frequency. I can find the other. High frequency, high gain divided by low gain equals high frequency divided by low frequency. And I just want to find out what's the expression for this 0, because it could be convenient when you make your design. It's not one extra degree of freedom. We have only 5 degrees of freedom, but this can be helpful to speed up your calculations. So, high gain, that is R2 divided by R1 parallel R3, that is R1 times R3, and give R1 plus R3. High gain divided by low gain is negative R2 over R1. Is equal to, we said, high gain divided by low gain is equal to high frequency 1 over 2 pi C3 R3 divided by F0 1, 0 2. And so we get that these are 2, and these are 2 cancel out, these are 1, and these are 1 cancel out, this positive, negative sign and negative sign cancel out, and we get something like R1 plus R3 or R3 equals 1 over 2 pi C3 R3 times 1 over F, no, yes, 1 over FC. That's complicated, very complicated, because we have to cancel R3 and R3 over here, then we have to move FC to the left hand side, and we have to move everything from the left to the right, and we get fz2 equals the second zero frequency as a function of a component equals to 1 over 2 pi C3 times R1 plus R3. And this is the second zero frequency. I cannot derive it just looking at the stuff. Zeros are more complicated than fours. And this is exact, it's not an approximation. This is exact because the op-amp separates this impedance from that impedance. When I told you the equation for this zero and this poles, I made an approximation. Because when you go to look at C1, you have C1 series with C2, but you can neglect it. It's a good approximation. On this side, there are no approximations. That is right, because the op-amp separates the two. Okay? So, we are almost done. We know how to determine all our components. We just need to refresh a little bit how to find the gains. So, this is my transfer function for buck converter. The DC gain is V in over V triangle. V in over V triangle is the DC gain, including the PWM modulator effect. Let's take the minimum, maximum, or let's guess this one. I want to design the compensation for the worst case. Worst case means I don't want my crossover frequency to go above given the limit. So the worst case, the most critical case is V max. Because if V decreases, everything goes down. So the crossover frequency moves to the left, it's not dangerous. And my T transfer function is this one. And I know the crossover frequency of C. Is equal to switching frequency divided by a factor of, let's say, from 6 up to 10. I have to admit that this story is not true. So, I know, I don't put the drawing scale, that my compensator should provide me with an integrated biology, one real zero over here, a second real zero on top of the two complex conjugate poles, then over here, a pole to cancel the output capacitor ESR, and another pole over here. You know that this pole and thing is here. I just need to find out how much is A1 and possibly A2. I don't need A1 and A2 and FC1 and FC2. But it's convenient to have all these numbers so I can make a check, final check. How can I find the gain A1? I have to find any point in this flat region, flat region on the asymptotic graph. If you look at the real, actual body start using SPICE, for example, or MATLAB, you will never see this flat region and this flat region. You will even wonder if there is a flat region over there, but asymptotically speaking, there is. If you want to find the A1, you have to pick any point on this flat region and determine the gain at that point, which could be a good point to find out this gain. Well, you have to see what is your given gain by the power stage, what is the wanted gain that you want in your T, and the difference in dBs, the ratio in terms of factor, gives you the gain A1. How much is this gain? V max divided by V triangle. Which point do we go to get from this wanted, desired loop gain? Well, this is a good point because we know this frequency, we know how much gain we want over here, and the ratio, how much gain we want, how much gain we have, gives me how much gain I need to store. And what if, this is not the easiest, the smartest way to do, but it can be done. What is the gain A2 I want to get? Well, A2 can be found by ratio 2 pole divided by 0 frequency equals A2 divided by A1. But it's not what I want to do because I want to check my calculation. So I can find A2 in a different way and I will check it eventually at the end, this A2 way. So for A2, I could say, well, this is the gain I want over here. This is the gain I have from the power stage, and the ratio of these two factors gives me A2. Well, how much gain I want at this frequency is easy because I know the crossover frequency. I know that this is a slope, a constant slope of negative 20 dBs per decade, and so I can find the gain very easily at any frequency. The only difficult part, not really difficult, but the only part that we didn't see yet in this class is how to find how much is this gain. This gain is not the V max divided by V triangle, because meanwhile, from this point, we came down. So this gain is lower. And we came down with a slope that is negative 40 dBs per decade. And so, do you remember how is the rule to find calculations from the balance plot using on the 40 dBs per decade the slope?
It's the same as the square.
It's almost the same as before. There is one extra square, that is frequency, the high frequency, the higher of the two frequency divided by the lower of the two frequency squared is equal to the high gain divided by the low gain. So if we want to find out this number, that is, because we know this frequency, we know this frequency, and the ratio of these two frequencies squared gives me the ratio of these two gains. Okay? So we can get A1, A2. We won't use A2. A2 is just there for a final check if we made too many mistakes in our calculations. Okay? Let's try an example. Say thank you. Oh, you don't say so, I do it. I won't give you a gift. My plan was to use as an example the circuit you have in the lab, the buck converter that you have in the lab and you worked with in open loop condition. You will design the compensator for this buck converter. You mount it and you check if it works or not. And you will do the same for the buck boost converter. So, let's start with the buck converter that has these specs. I need the specs to design, to put numbers in my transfer function. How much is the inductor value for the buck converter in the lab? 220 microamps. How much is the output capacitor for the buck converter? 185. And it has a zero frequency, this capacitor, due to its ESR, that is around, did you measure the zero frequency? Yes, maybe using a ripple, somebody of you did it. It was around 50 to 60 milliohms. And the zero frequency turns out to be around 3 kilohertz. It's not the best capacitor you can find out there, but it's not the worst neither. Load, we don't need the load value because if load changes, the only effect is, if the load changes not too much, the only effect is to change the Q factor, the damping factor of our complex conjugate poles. If the load becomes too light, we go to DCM. Too bad, DCM, the model changes dramatically. Then we need the switching frequency. How much is the switching frequency? 50 kilohertz. And you don't know it, I have to provide it with this information. The triangular V triangular is 3 volts. That is the peak-to-peak voltage of the sawtooth waveform. And the V reference is equal to, I think it's 2.5 volts. Not so sure, but should be 2.5 volts.
Without offset, the triangular is without offset in the V triangular.
We don't care if there is an offset or not in V triangle. There is an offset. You can measure it with your scope. There is an offset in V triangle. It's the sawtooth. But we don't care about it because the compensator, the type 3 compensator, is integrated, has an origin in the triangle. So this offset is just reduced by the gain, the high DC gain of my compensator. Okay, 2.5, I think everything is there. I want an output voltage, 10 volts. The input voltage goes from 15 volts up to 30 volts. And in your final exam, you will have this kind of specs.
50 kilohertz.
What is it? This is switching frequency, 50 kilohertz. You won't have this switching frequency. You will have to select it, choose it. You won't have neither the zero frequency. You will have to tell me what kind of capacitor you want to use. It's just a number between a couple of kilohertz up to 10 kilohertz or so. But everything else is more or less like a typical design exam. So, let's start to put numbers. We need to start to draw the buck transfer function and put numbers in it. Gain. How much is the gain, the DC gain of our buck converter? That buck converter.
30 over 3.
30 over 3. What?
As a gain.
What? Dimensionless. Volts divided by volts is dimensionless. So the gain over here is, the maximum gain over here is 30 volts divided by 3 volts. That is equal to how many dBs? 20 dBs. Don't use it, the dBs in this case. Then, the two complex conjugate poles. What's their frequency? One over 2 pi square root of LC out. You know the value of L. And in your exam, the value of L is what you designed, and the power phase of designing. How much is C naught? You have an idea what is C naught from the ESR. In this case, it's given because of the existing circuit.
340.
What? Hertz. Zero frequency. The zero frequency is the zero of your capacitor. So if you pick the capacitor that has imagine you pretend that you use a capacitor that has zero frequency at 3 kilohertz or 5 kilohertz, this will be 3 kilohertz, 5 kilohertz, whatever it is. In our case, this is a real capacitor. Fz is 3 kilohertz. Please, pretty please. I don't need to tell you, but who knows. Kilo, the prefix kilo is lowercase. It's not uppercase. Thank you. That's it. Those are basically all the numbers we need from the power stage. Just for double check at the end of our calculations, I would like to have also a gain over here. And a little bit better.
0.13.
Yeah. Okay. Did you need your calculator to find out this number? No. That's easy because it's 3 divided by 3 kilohertz divided by 340 hertz. That is 3 kilohertz divided by 30 hertz. That is 3 kilohertz divided by 300 hertz is 10 times. Well, it's not 300, it's 340. So we have to remove a little bit then, more than 10%. Let's say 10%. That is not 10 by 9 times. 9 squared, because this is totally viscous package log, so we need to square the frequency ratio. 9 squared is 81. Let's say 80, because we already approximated a little bit too much earlier. And so 10 divided by 80 is 0.125. Well, it's not really 125 because it was 340, not 330, so a little bit more than 0.125, 0.13. Oh, by the way, that means that if this is my 0 dB axis, this 0 will be below the 0 dB axis, but I didn't put any scale on the graph. This is what I get. What I want is something like this. The gain, integrative gain for T, and the only number I have to specify is the crossover frequency. How much is my crossover frequency? How much do we want to set that?
50 over 10 or
50 kilohertz divided by 6, quarters more. 8, quarters more. Then, which one do we take?
8 is divided.
Let's take 8. So, my crossover frequency will be switching frequency divided by, let's say 8. 50 kilohertz divided by 8 is 6.5. Does it have any meaning, this 0.25? No, because it's just approximation. If you tell me 6 is okay, if you tell me 6.5 is okay. Don't be too romantic about these decimal numbers. Something just 6 kilohertz or so is okay. So now we need to find out our compensator transfer function. My compensator transfer function is, because it's not on in scale what I am drawing now. In any case, it has an integration characteristic, so a pole at the origin. It starts with an initial slope of negative 20 degrees per decade, comes down, and at this frequency, a factor of 2 before my complex conical pose, I set in the first 0. And the first 0 is given by pole frequency divided by 2. So, 340 Hz divided by 2 is about 100 and what? I already had doctors to tell the quantities of the substances. Take this pill by 200. 200 what? 10 liters, micrograms, whatever. I know that this is absolutely useless, but makes me sad. 170 hertz. Then we have another pole zeroed in at 340 hertz. Those are my numbers to design the compensator. And then here at 3 kilohertz we have a pole. So the gain stabilizes level off. And after the crossover frequency, at least 3 times above the crossover frequency, I have the closure pole. And the closure pole will be 3 times higher than this. This is 6.25 kilohertz times 3 is 18.75, let's call it 90 kilohertz. And we have, as a check for your calculation correctness, you can check if this pole is at least 2 times lower than the switching frequency. Switching frequency is 50 kilohertz. This is less than 1/2 of the switching frequency, is okay. If you don't like 19 kilohertz because you are superstitious and you don't like the number 19 and you want to move it to 22, that's okay. I don't like it too much. What are the advantages and disadvantages of moving this threshold pole up and down? If you move it up, you have less filtering, less attenuation of the noise, switching noise frequency, but you move away your pole from the crossover frequency, that means your phase margin improves, increases. If you move your closure pole down, you better attenuate the switching frequency, but your pole becomes closer and closer to crossover frequency, and your phase margin is decreased, is evolving, because a pole has its effect on the phase starting from far above, far below the pole frequency. 1 decade before, the phase margin, the phase is 5.7 degrees. We approximate to 0. We say that the pole has a phase effect that starts 1 decade before and then 1 decade after. But actually it's the arc tangent. The arc tangent of 0.1 is 0.1. And 0.1 radians. And 0.1 radians is 5.7 degrees. So, 19 kilohertz is fine. If you don't like it, you want 22, put it 22. Okay. Don't go too high, don't go too low. We need to determine these 2 gains. We need to determine this gain and this gain as a check. We don't need it, we don't use it, but we will check it as it is. This gain is determined checking, observing what is the given gain by the power stage and what is the needed gain. Oops, wrong color. What's the needed gain over here from the transfer function, the T transfer function? How much gain do I need over here?
We have the high frequency.
Sorry?
We can find it because we have the high frequency, low frequency.
We have high frequency, low frequency, we have low gain, we need the high gain, and this is a slope that is 20 dB per decade. So, my high frequency is 6.25 kilohertz. My low frequency is 340 hertz. And so the gain I need over here is 6.25 kilohertz divided by 340 hertz. $18.4. This is the gain I need. This is the gain I get. And so, the gain I have to provide, the gain A1, is equal to Very good. I would make 18.4, that is this gain, minus 10 equals 8.4.
They are not dBs.
They are not dBs. They are. How many times is, more or less, 49.5 dBs? 50 dBs. How many times? 300? It's nothing to do with this problem.
49.
49.6. 50. 300 times is okay. Good work. Thank you. So, this gain is 1.84 times. And observe that in both converters, CCM, Bode's model, this first gain is quite low, or quite low. And how much is this gain? We don't use it for design. We use it just for double check. This gain is equal to this, the gain I want, divided by the gain I get over here. How much is the gain I want? Same story as before. High frequency divided by low frequency equals high gain divided by low gain. High frequency is 6.25 kilohertz. Low frequency is 3 kilohertz equals high gain divided by low gain. This gain divided by this gives me the gain I need. So this gain is about 6.25 divided by 3, that is 2.1, 2.08. The actual gain I have here is 0.13. And so 2.1 divided by 0.13, let me do it, please. Make this all close the clouds. That means make it in your head. That's easy. Get your calculator, please. 0.26. No, 16. Going better, yes. Come on! It's 21 divided by 14. 21 divided by 14, there is a 7 factor. So it's like 3 over 2. It's not 3 over 2, it's 30 over 2, that is 15. Well, this is not 0.14, this is 0.13, so it's 7% more. And the 7% of 15 is 1, and maybe more than 1, but it's 1. So, total is 16. How much is it? 16 point? Okay, here gain is 16 times. Okay, all the numbers are there, and we can just use our equations we derived earlier to find out the values, the component values. We start to assume a value for C1. And as usual, C1 go from 100 picofarads or less, a few tens of picofarads, to 1 nanofarad or less. So C1, 100 picofarads is my choice for today. I forbid you from using 100 picofarads in your final exam. If you use 100 picofarads, I will consider it wrong. Why? Because otherwise everybody will use 100 picofarads, and I will get bored and bored reading all your exams with 100 picofarads. Come on, give me some fun.
99 picofarads.
99 picofarads does not exist. Yeah. Actually, it exists because there are many 100 picofarads, or some of them that have an extra capacitor from 99 picofarads. So we can write, what is the first equation we can use with this number? is F2 closure pole equals 1 over 2 pi C1 times R2. That means, how much is the closure pole? What frequency did we choose? 19 kilohertz equals 1 over 2 pi C1 is 100 picofarads times R2. And solving a very difficult equation, R2 equals 1 over 2 pi times 19 picofarads, no, 19 kilohertz times 100 picofarads. Come on, it's easy. Try to make it in your head.
Over 1,000. That's
How much?
4 over 1,000, so 1 over 250.
Yeah, you are probably 25% off. Not bad.
It's 20 times 100 is 2,000. So more
20 times
1,000 100 is 2,000. So
Okay.
we have more or less 2 megahertz times 1 pico. So it's 2 times 2 milli.
one complication, one difficult part making your mental math is that if you try to make it in English, it's not difficult. Usually when you make mental math, you use your native tongue. You use the tongue you learn the calculations. So you can think in Italian, please. Come on. Start with the difficult part. Don't start multiplying here by 100. Just does not give you anything. The only point of multiplying 100 by 1.19 kilohertz is that you can say this is 1.9. You cancel this 100 and this pico becomes nothing. That would be the reason for making this calculation first. But that's not changed too much. 2 pi is 6. More or less, it's within 5%. This is 20. 6 times 20 is 120. Oh, by the way, 19 is 5% less than 20. 2 pi is about 5% more than 6. And so these 12s cancel out. Nano times kilo is micro. Micro goes up and becomes mega ohms divided by 120. 1 mega divided by 100 is 1 mega ohm divided by 100 is. Oh, 12, not 120 because we moved to 1.9. 1 mega divided by 12 is 1 mega ohm divided by 10 is 100 kilo ohms. Well, it's not 10, it's 12, but the reciprocal of 12 everybody knows. The reciprocal of 1.2 is 0.833333, so this is 82 kilo ohms. Okay, end of mental math for today because otherwise you will be exhausted for all week long. Come on, you will be engineers, not poets, not lawyers. Talking about lawyers, I have a classmate, high school classmate who is a lawyer, and his specialty are contracts between large companies. He does not go to the court fighting, etc. Just checking contracts, etc. And what he needed was a capability to make assessment, a fast assessment of the conditions on a contract, because the other part was suggesting, oh, let's change these with numbers. Let's change this percentage to this value or this value. And he needed to make a very fast calculations to check if the proposal, the other part was okay or not acceptable. I taught him how to divide in his head using Taylor series without telling him that it was Taylor series because he's a lawyer. He was so happy to learn this trick of using the percent of the denominator changing to simple numbers and correcting with the percent. He was so happy. He invited me, he treated me with a very good dinner in the best restaurant in Torino, just because I gave him a very powerful instrument to make calculations. So you are engineers, you have to do it for free.
In order to have a friend who can.
So you can have a friend who can. Okay, 82 kilograms. R2 is equal to 82 kilograms. That's it, finished, nothing more. Even if your calculation gives you something like 83.3, whatever it is, now this is your reference rate. Is the normalized rate. Then we can find C2. C2 is associated with the first zero. This is my choice. If you want to have C2 associated with this zero, you may guess. In this case, C3 will have this zero, and you have some other equations in between. Probably C2 associated with zero is the easiest way to do it, but nothing changes if you want to change to derive your equations. C2 is equal to 1 over 2 pi times the frequency of the first zero, that is 170 hertz, times R2, 82 kilos. Use your calculator.
Okay.
I want to finish before noon.
Ten
10 nanofarad, 11 nanofarad.
11 or 12. Maybe 12.
Okay, obviously I know how much it was going to be. This is the standard, this is the type 2 compensator, like a type 2 compensator. So the ratio of pole divided by 0 is equal to the ratio of the capacitances. We have 19 kilohertz divided by 170 hertz, that's about 100 times, a little bit then more than 100 times. And so the ratio to capacitance will be 100 times. 100 picofarads times 100 is 10 nanofarads. A little bit more, 11 nanofarads. So C2 you can take 10 nanofarads or 12 nanofarads. If you take 12 nanofarads, your zero moves a little bit lower. It's not tricky. You can take whichever you want. 10 nanofarads is fine. Then we have R1. R1 is equal to A1 R1 equals R2 divided by A1. There are two negative signs missing, but it's okay. R2 is equal to
47.
no, R2 is equal to 82 kilos. I1 is 1.84 times
44 kilo.
Okay. 47 kilograms. Is it okay? Okay, 47 kilograms. Be careful. This resistor must be very precise, 1%. I didn't say anything about the precision of R2. 5% is fine. I didn't say